Hello there, welcome to the presentation about the principle of mathematical induction. Now this principle is really a process that helps us to offer a convincing proof to a given statement. It comprises of three aspects to it, of which I call the TAP method. And really in this video I want to clarify what the TAP stands for, and to help you structure your proof in a way that will agree to the principle of mathematical induction. Okay, so we are given a statement, suppose statement A, okay, and we need to prove this given statement A using the TAP method. Okay, what does the T stand for? It means you need to test the given statement for the base case. Okay, so you test the given statement for the base case. Okay, now this base case differs from question to question or from statement to statement. It can be n equal to 1, n equal to 2. For instance, if here you're given that this statement holds for all n element of natural numbers, then base case will be the first natural number n equal to 1. However, if you're given an inequality in the statement to say this statement will hold for all n greater or equal to 3, then it means your base case will be n equal to 3. You start proving for n equal to 3 for that given statement, right? And we'll do two examples as part of this video to help you understand how the TAP method works and really how to go about using the principle of mathematical induction, right? So just hang in there, we'll get to a much more clearer picture of what this process entails. So that is the first letter there, T. You're testing the given statement for the base case. A, you are assuming that the given statement is true for n equal to k, where k is an element of natural numbers. Okay, so this is an assumption step. Okay, so it's an assumption, or you assume that the given statement is true for n equal to k, where k is an element of natural numbers. Okay, and you show mathematically that it is true for n equal to k, just like you did here for a numerical value of k. So k is any natural number there, right? So after this assumption step, you now prove, okay, that is the letter P, you prove that the given statement is true for n equal to k plus 1, and k still is in the same set, natural numbers. All right, so since k is arbitrary or is a random natural number, and you're proving that it is true for any other chosen number after that or natural number after that, then it must be true for all the natural numbers. Okay, so therefore you can conclude after performing this three steps and say, since the given statement is true for the base case for n equal to 1 or n equal to 2, and true for n equal to k plus 1 if it is true for n equal to k. So it is true based on the assumption that you are saying it's true for n equal to k. Then it follows that statement A is true for an element of natural numbers. basically that is the structure for mathematical induction, whether you're dealing with summation or divisibility. And I will offer, examples for both, approaches or both types of problems that you will get. Okay, so this is really the essence of what I wanted to start with. And now let us move on to our first example, that is under summation, and example 2 will be under divisibility, and that will help you unpack this process. Let's go for it. All right, so here is the example under summation. Prove using mathematical induction that n squared plus n is even for all n element of natural numbers. Since this is n element of natural numbers, our base case will be n equal to 1, the first natural number, and this is the statement that we want to prove. Okay, and it must be true for n element of natural numbers. What is the first thing we need to test? Okay, test the statement for the base case for n equal to 1. So we go 1 squared plus 1 is equal to 2, which is even, right? And therefore the statement is true for n equal to 1. We're done with the first letter and the step method, the T. Now we go to the assumption step, where we're going to produce the inductive hypothesis to say, assume that the given statement is true for n equal to k, where k is an element of natural numbers. Okay, so we assume that the statement is true for n equal to k, where k is an element of natural numbers, such that this happens. K squared plus k is equal to 2 times t, or product of 2 and any other number, whether it's even or odd, you'll always end up with an even number. So this is an even number where t is an element of natural numbers. Okay, so that is the inductive hypothesis, that it is true for n is equal to k. Now we need to prove the statement to be true for n equal to k plus 1. Okay, so the proof, we're going to use our inductive hypothesis now here to see how we can work with that. Right, so we know this, k squared plus k is equal to 2t. This is by assumption. Okay, now when we sub in k plus 1 into this expression here, we have k plus 1 squared plus k plus 1. What is this equal to? This is k squared plus 2k plus 1 plus k plus 1. Right? Now we need to rearrange this so that we can make use of our inductive hypothesis here. So we're gonna group the k squared and the k. So this is equal to k squared plus k plus 2k plus 2. Right? This two terms, k squared plus k, gives us 2t, right? Plus 2k plus 2. Now you notice something. We can factor out the 2 here. This is equal to 2 into t plus k plus 1. By the same logic here, we know that this product will be an even number, k, which is even for all t and k element of natural numbers. Okay, now we can conclude. Therefore, since the statement is true for n equal to 1 and n equal to k plus 1 if it is true for n equal to k, we can now say therefore by the principle of mathematical induction, the statement, okay, I'm gonna go now here, is true for all n element of natural numbers. Okay, and that takes care of this summation example. Let's go to the divisibility example and see how we can unpack it using the principle of mathematical induction. Alright, here is the divisibility example. Use mathematical induction to prove that n cubed minus n is divisible by 3 for n greater or equal to 2. Here's our statement. We need to prove divisibility by 3 of this given expression for n greater or equal to 2. So our base case here will be n equal to 2. Okay, our lower bound or our lower end point of this restriction on the natural number set. Good. So what do we need to do? Test the given statement for the base case. So test the statement for n equal to 2. Right. So we go 2 cubed minus 2 is equal to 6. And we can be explicit here, even though we know it's divisible by 3, we can say it's 3 times 2, just to bring out the 3 there, right? Which is divisible by 3. Okay, so therefore, the statement is true for n equal to 2. We're going now to the assumption step where we talk about the inductive hypothesis. Okay, so we assume that the statement is true for n equal to k, where k is an element of natural numbers. So we mean k cubed minus k is equal to 3 times t, where t is an element of natural numbers. Right. So this is the inductive hypothesis. Are we ready to prove? Yes, so prove that the statement is true for n equal to k plus 1. Okay, so now let's do that. The proof. I'm going to apply the inductive hypothesis there. K cubed minus k is equal to 3t. This is by assumption. Alright. So if we sub in k plus 1 there, alright, it's k plus 1 cube minus k plus 1. This will be equal to k cube plus 3k, okay, plus 3k square plus 3k plus 1 minus k minus 1, okay, minus 1 if you distribute that, okay. And then what then happens? We want to make use of our inductive hypothesis. So we need to group this guy with that guy. So this is equal to k cubed minus k, right, plus 3k square plus 3k. Well, 1 minus 1 disappear. But this equal to 3t. This is equal to 3t plus 3k square plus 3k. What can you observe? Factor of 3. That is the highest common factor there. So we take it out. 3 into t plus k square plus k. Well, definitely this is divisible by 3, okay, which is divisible by 3. Okay, therefore, since the statement is true for n equal to 2 and true for n equal to k plus 1 if it is true for n equal to k, it follows by the principle of mathematical induction that the statement is true for n greater or equal to 2. Right, that was the condition that was given. So this takes care of this example, and it takes care of this presentation on mathematical induction. I believe I was able to be helpful and available to you. If you need to, you can go watch this video to make sure that you understand what just happened. All right. So thank you for watching and thank you for tuning in. Make sure that you please subscribe so that you help this channel to reach a wider range of audience and continues to help people out there. Keep well. Thank you.